Now let us take a specific example from the IRC 37. We have all these layers in our pavement. We have a modulus value, we have a Poisson's ratio, and we have thickness parameters that we usually use for design. So what is the variability associated with each of these parameters, right? So there are some literatures which have measured all these things on a given pavement system, and they have quantified how much will be the variability for each of these three parameters that we usually use for design. With Poisson's ratio we will not be able to observe, but modulus and thickness, yes. So if I take a particular layer, right, this is a sub-base layer, you can see here that this is the thickness in meters, so it is 150 mm. You can see how much is the variability. So this is 150 mm. Okay, my line is not. If I am trying to draw a line at 150 mm, you can see that it has varied around it. In some cases it has gone even closer to 100 mm, and in some cases it has gone closer to 200 mm, but this is like once in a while, but in most of the cases it is around 150 mm. Similarly, if you see it for asphalt layer, you can see that it is again varying over a range, right. So this is the amount of variability that we can observe in layer thickness if we go measure it for a pavement, because it is practically impossible to construct a pavement for exactly the design thickness. The best we can do is to minimize the variability, but we cannot avoid this variability, right. So this is for the layer thickness. Again, if I am representing that in the form of histogram for the total asphalt layer, again for 1 kilometer section, if I am taking measurements at 1 kilometer section and drawing a frequency distribution, you can see there are few sections which have values as less as like 245 mm, some greater than 285. So the range is somewhere between 245 to 285 mm. Again, we are not sure whether this is the exact range because it is less than 245, but let me just assume that it is going to vary in this range, right. So this is the amount of variability that we are seeing for the layer thickness for the bituminous layer. Similarly, we can also see the variability for sub-base layer. Again, you can see it varies from 85 mm to 200 mm, right. So this is the amount of variability that we see. Again, for each layer when we measure, we will be able to observe the degree of variability. So now if we take a system, let us say it has 4 layers, again one is your subgrade. If a system like this is taken which has 100 mm surface course, 150 mm base course, 400 mm sub base course, right, and if I am able to measure the thickness, this could be probably the variation in thickness that we can observe for each of these layers, right. If I am plotting a histogram of this variability, let us say if I am plotting a histogram, most of the cases we might be able to approximate it with the normal distributions. In some cases we will also observe different other kind of distributions like log normal or beta distribution or extreme value distribution. So different kind of distributions may be observed, but many times we will be able to approximate it with a normal distribution. So if I am assuming a normal distribution for this case, this is the amount of variability that you can see for each layer, right. So this is the surface layer, this is the base layer, and this is the sub base layer, right. So as we go to the surface course, we are able to minimize the variability, but in a base layer the variability is large. So this variation that we observe in field, we can plot it and we can approximate it with any appropriate distribution. So we know that a normal distribution is usually characterized by 2 parameters, one is the mean value and the other is standard deviation. So using these 2 parameters, we will be able to describe the variability for any parameter. So if you look at this, this is the modulus for a given mean and coefficient of variation. So, using the mean and standard deviation, we compute the coefficient of variation just to have an idea of how much is the variability of a given given parameter with respect to its mean. So, this coefficient of variation is usually defined as the standard deviation divided by mean into 100, right. So, the amount of variability that we see in a pavement system is quantified in terms of this coefficient of variation, and it is always associated with the mean value. So, if I know a mean value, let us say my target is 2500 megapascal for a given layer, if my E value is 2500 megapascal, this I can use it as my mean value, and depending upon what is the expected variability for this particular layer, I will be able to generate this kind of a distribution for any given input parameter, right. So, only if we are able to identify a distribution, then it becomes simple to incorporate this into the design process, right. So, now let us see what are the coefficient of variation and mean values for different layer thickness and modulus values for different layers. So, if I take the layer thickness, the bituminous surface, this is the range for coefficient of variation. So, the typical value which is used is around 7%. So, there are some other studies as well which report the COV to vary between 3 to 18%, right. And for a bituminous binder course, which is kind of like your DBM, the coefficient of variation varies from 11 to 16 in one case and 5 to 15 in another case. So, we assume somewhere around 10 for this layer, we assume 7 for this layer, and if it is a granular base course, it is 10 to 15 or 6 to 17. So, it is again around 10 to 12. For a granular subbase 10 to 20. So, we use a higher value because even here you could have seen as we move to bottom layers, the variability becomes higher, right. So, we use a higher coefficient of variation for the low lying layers. So, this is the range of coefficient of variation, and mean could be any target mean value that we desire. Then if we look at the elastic modulus, for bituminous layers it is between 10 to 20%. This value is nothing but coefficient of variation, which is standard deviation divided by the corresponding mean value. Again another study 10 to 40%, for granular base 10 to 30 or 5 to 60. So, it is usually 20%. You can see thickness is better approximated. So, we have less coefficient of variation values for the layer thickness, but when it comes to modulus, it is usually around 20%. Even for your base and subbase layers, when we measure CBR, we use a coefficient of variation of 20, right. So, this is the typical degree of variability that we observe for most of these layers, and these are all values reported from different studies. Now, if we look at other traffic parameters like we discussed earlier, we have traffic volume. So, again if I do a spot speed study at different locations, we might have variability, especially if you use a sampling methodology rather than surveying the entire population. Similarly, contact pressure, again wheel load, axle configuration, right, the spacing between the wheel, vehicle damage factor, the lateral distribution factor. So, like that there are many parameters with respect to traffic also. Subsequently, we will see 2 or 3 parameters. So, this is the traffic volume, it is the average traffic given in terms of AADT, right. So, this is calculated at different locations, this is in fact measured at different locations. So, location V5, V6, V4 and V7, and it is done for different days in a week, right. So, for a given day you can see how it varies from different locations, right. So, why does this become important, right. So, if I have a 100 kilometer stretch of road, let us say I have 2 intersections here, probably we assume this to be one homogeneous section, we assume this to be another homogeneous section, we assume this to be another homogeneous section. So, let us say I am considering 5 traffic surveys here, 5 traffic surveys here and 5 traffic surveys here, right. So, let us say we do different design procedures for this homogeneous section 1, this section 2 and this homogeneous section 3. Okay. So now if I get 5 values here, and let us say there is some degree of variability in all these 5 AADT values, so let me call this as 5 AADT values. Which AADT among these 5 values will I use for design? Will I use an average value, or will I take the maximum value or minimum value, right? So that is where this concern comes in. So if I measure at different locations like this, and if each of them are going to show me this much amount of variability, which parameter will I use for design, or how to consider all this variability into my design process and use one or a few representative values, right? That becomes the major challenge here. So now this is the AADT variation at different locations for a given week, and if we are computing the coefficient of variation, this is the coefficient of variation for these different locations, right. So the variability is large for some locations and less for some cases. So like we quantified the coefficient of variation for material parameters, we will be able to do the same thing for traffic related parameters also. And this is the percent of daily traffic for different hour of the day. So when I am doing a traffic survey, we have spatial variation, we have hourly variation, we have daily variation, right, and again all monthly, yearly, all those things will come in, right. So all these things will come in. Again all these things are going to depend upon the type of vehicle. So if I am going to measure the percentage of daily traffic, it is going to vary in different manners. If I take rural cars, this is rural cars. If I am going to measure it for business day trucks, it is this symbol here. So if I use it for urban cars, this is this urban cars, right. So each of them have a different pattern. Again, how am I going to take all of this into my design? Am I going to approximate or design each of them separately considering their variability? How is it going to be taken into account in the design process, right. So this is another set of variation that we are seeing here with respect to day, and this is again the weekly variation with respect to the vehicle type. So we are all aware of this the different factors which contribute to variability in traffic volume, right. So how do we consider all these things, how do we combine all this variability and use a representative value which will more closely represent the or more closely represent the damage that is experienced by the pavement, right. So that is the major challenge in the design process. Again we have tire pressure. This is from one of our studies which we have conducted at a specific or a few specific locations in Chennai. So the tire pressure data was collected for 100 vehicles. You can see here this is for the front axle, which is single axle single wheel. This is single axle dual wheel, tandem axle dual wheel. You can see the minimum and maximum. So minimum is as low as 551 and the maximum goes up to 965. Similarly for single axle dual wheel and tandem axle. So if I am plotting the tire pressure value for the single axle, I am getting a range of value, right. So this is the degree of variability associated with this particular parameter. Similarly single axle dual wheel and tandem axle. Similarly if I am plotting the axle load for these vehicle categories, the range of variability is given here for single axle single wheel, for single axle dual wheel and tandem axle dual wheel. So this is another parameter from the traffic perspective. The next is the dynamic load. So what is dynamic load? For pavement design, we usually use a static axle load. The static axle load is nothing but the load transfer from the vehicle to the pavement when the vehicle is in a standstill condition. So we use a weigh pad, or we even get the data from weigh bridge where the vehicle is standing and the load transfer is measured. So the vehicle is there in a standstill condition. But in real scenario, when the vehicle is travelling on the pavement, it is not in a standstill condition, the vehicle is in motion. So depending upon the different actions that we perform on the vehicle, the load transfer is going to vary. The different maneuvers that we observe for a vehicle are acceleration, deceleration and braking. So what is this acceleration? Let us say we are moving at a constant speed, right, and suddenly we want to increase the speed. So when we step onto the accelerator and when the speed is increased, we are suddenly pushed back. when you are traveling in a car and when you suddenly accelerate, you should have observed this, right. Similarly, when we are traveling at a constant speed and when the brakes are applied, when the brake is applied suddenly, you should have observed that we tend to move forward, right. So, this is a braking phenomena that we observe. So, during each of this, similarly you can say deceleration when you are trying to slow down. During each of these phenomena, Donia has done a lot of studies on different types of vehicles, and she has simulated the load transfer that is observed from each of these phenomena for a given static load. So, she has assumed a static load of 71.3 kilonewton. So, when this load is applied, this FZFA is the force in the Z direction, which is nothing but the vertical direction for the front axle, right. So, when a static load of 71.3 kilonewton is applied to a given vehicle and the different maneuvers are simulated, this is for a braking phenomena. She has seen that the wheel loads will go up to 131.5 kilonewton. So, at a moment when this braking phenomena happens, the load is as high as 131.5 kilonewton. So, even the axle load which we assume it to be a constant for a given vehicle is not a constant, but it varies depending upon these kind of maneuvers, right. So, this is one kind of variability. Now, there are other variabilities associated with the design methodology as well, right. Now, let us take IRC 37 design procedure and let us see how reliability is addressed in this particular design procedure. If you look at the IRC 37 procedure, you should have seen that we use single value for all input parameters, right. So, we have thickness, modulus, Poisson's ratio, axle load, tire pressure. For all these parameters we use one value, and typically we tend to resort to use a mean value, right. So, it is one single value for all input parameters, and even the design procedure is deterministic. We give all the input parameters, we get critical strains corresponding to this combination, and that is used in the distress transfer function, right. So, in the transfer function you can see that it is specified for two different reliability levels. We have one equation for 80% reliability and another equation for 90% reliability for both subgrade rutting and fatigue cracking in bituminous layer. So, this is the only aspect through which reliability is incorporated into the design procedure, right. Now, if you look at these NF and NR values, we are going to get one value, one single point value based on this design procedure. But we have seen that there is variability with respect to all the input parameters, even the constants that you use here, right. These constants are calibrated for a specific, from a specific set of study at a specific location or at few locations, right. So, there is going to be variability associated with each of these input parameters as well. So, these constants that are used here or even these constants which are used in these equations. So, considering all that, if all of them are incorporated, what will be the degree of variability in my output, right. So, for a pavement structure, there are two failure modes which are considered, like we have defined earlier. One is fatigue cracking and other one is rutting. Typically, the assumption is that they are independent of each other, right. If a pavement fails by rutting, not necessarily that it is going to fail by fatigue cracking. Though there are a lot of studies which talk about this creep fatigue interaction and all those things, for the moment let us say that they are independent of each other. Then they can be considered to operate in series, right, wherein this whole system, let us say this is my whole pavement system. This system is considered to fail only when any one of the component fails. So, either it can fail by rutting or it can fail by fatigue cracking. When one of these distresses happen, then it is said that the pavement has failed. So, the total reliability of the system is given as the reliability of fatigue cracking times the reliability of rutting, so that if 1 becomes 0, then the reliability of the system will become 0. This is one assumption based on which the reliability for the IRC 37 design procedure can be specified. So, now considering the variability of all these input parameters, if I consider the rutting and fatigue life in the pavement, you can see this is how it varies. So, it is not a given value right. We will not get one NF and one NR value, but this NF and NR value are going to be a distribution rather than a single point measurement, and this considers the variability of all these input parameters. Later, as I said 2-3 lectures down, we will go through a procedure wherein we will be able to arrive at this kind of a distribution for the rutting and fatigue life for the pavement. So, this is for rutting and this is for fatigue life. Okay. So, ideally we should be getting this, but what we get in IRC 37 is one deterministic value. So, this is an overview about reliability, its consideration, the factors contributing to reliability in pavement design and their considerations in IRC 37. So, I will stop this lecture here. In the next lecture, we will talk about reliability in the AASHTO 1993 design procedure in specific. Thank you for your time.